Today we're going to tell you about something really amazing we did in our lab. We managed to make water out of thin air.
You mean like this?
Not exactly, but the principle is similar. We managed to cool a surface enough in order to have dew form on it.
So why do we need to make water from the air?
In remote places, such as Africa, many people are not connected to water infrastructure and don't have other ways to access clean water. Our goal is to provide a low-cost apparatus that can be utilized to get a small but life-saving amount of water.
By using our dew collection device, you can make in one night all the water needed for a baby for an entire day. Think about it as a solar panel, but instead of providing electricity, you get water, the substance of life.
We made a cold surface using nothing more than the atmosphere.
Actually, we bypassed the atmosphere.
We managed to cool a surface down to 8 degrees Celsius less than the ambient temperature, and by doing so, our apparatus was able to collect up to 250 milliliters of water per night from a surface of 0.64 square meters.
And in many of the nights, when there was no dew collected on any other surface, we still managed to collect some dew.
But before we can tell you more about how we designed our device, we need to explain some basic ideas about heat transfer and dew.
There are three types of heat transfer: radiation, convection, and conduction. Let's see some examples.
Convection is a process of particles of different temperatures moving from one place to the other. Usually hot particles will rise and cold particles will descend. Conduction is heat energy transitioning through materials. In this case, the particles stay in place, but energy is transferred from one particle to another. Every material conducts heat, but with a different efficiency. For example, aluminium conducts heat 10,000 times better than air. Lastly, radiation. Radiation is a transfer of heat by electromagnetic waves. The most common example we all know is sitting next to a campfire on a chilly night and warming up. All materials above the absolute zero, which is minus 273 degrees Celsius, radiate heat. This phenomenon is called Blackbody Radiation.
The wavelengths of the radiation depend on two major parameters. First is the type of the material itself, and the second is the temperature of the material. Looking at the Stefan-Boltzmann law, we can see that the wavelength changes like the temperature to the power of 4.
Which leads us to our next subject, radiative cooling.
We said that every object above the absolute zero radiates heat. That, of course, includes the Earth and the Sun.
We can see in the graphs the radiative spectrum of both the Sun and the Earth. It can be seen that most of the Sun's transmission wavelengths are in the visible spectrum, and there is some energy transmitted in the infrared and the ultraviolet.
However, the Earth's radiative spectrum is only in the infrared, so we can't see the radiation of the Earth, but we can feel it.
Now let's talk about the atmosphere. The atmosphere is a layer surrounding the Earth that consists of many gases. Each of these gases absorbs different wavelengths and creates heat. A surprising fact is that there are some wavelengths that the atmosphere does not interact with. So these waves can go all the way to outer space. This is called the atmospheric window.
A material that radiates heat in the wavelengths of the atmospheric window will exchange heat with outer space, which is very, very cold, about minus 270 degrees Celsius cold.
So, in order to cool our system down, we need to choose a material that radiates heat in the spectrum of the atmospheric window, and on the other hand, we need to isolate it so it barely exchanges heat with its surrounding through convection or conduction. Our perfect material will absorb no heat from the sun and will radiate heat in wavelengths of 8 to 13 micrometers. This kind of material is called a selective emitter.
One thing that is really important for our system is clear sky. We don't want anything interacting with the radiation before it gets to space. So, our system will not work at home or in a shaded forest as well. With an ideal selective emitter that is perfectly isolated, the apparatus should get as cold as the outer space. There is a group from Stanford that, using a selective emitter and a vacuum as an isolator, managed to get down to minus 50 degrees Celsius, but it's very complicated and expensive to achieve.
Now you are probably asking yourselves how radiative cooling relates to dew collection.
Well, there is one more thing we need to tell you about, and this is dew point.
The dew point is a temperature in which water will condense or change from gas to liquid. This is why we don't always see dew, but after a cold and clear night, we can see dew all around us, those little drops on cars and plants.
The dew point is affected by two parameters, radiative humidity and the ambient temperature. We can't change them. However, we can try to get the temperature of our surface down to the dew point by radiative cooling.
Let's talk about our system. Our dew collector sits on a frame made out of wood, and its surface is at a 30 degrees angle, which is the best angle for dew collection. This way the surface is directed at the sky, but gravity will still pull the water droplets down towards the pipe in which they are collected.
The dew collector's surface is built from a piece of HDPE, which is a type of plastic that is clear to most of wavelengths. The upper side of the HDPE is left untouched. This is the side on which the dew forms. We painted the lower side with our selective emitter, barium sulfite, mixed into an ordinary white paint. Our recipe is equal amounts of white paint and barium sulfite. We found barium sulfite to be a great selective emitter for our needs. We used 5 coats of this mixture and put it on a good isolator, wood. Then we put it in another isolator, foam plastic, and then we wrapped it all with aluminum foil, which is a good reflector. All these layers reduce heat transfer from the environment to the system. We also tried to minimize the amount of direct sunlight that gets to the system. This was done by using more reflectors and putting the apparatus in the area that is shaded from the sides.
And now for the results. We managed to get our surface to a temperature that is, on average, 8 degrees Celsius lower than the ambient temperature, and collected up to 200 milliliters of water in a single night. Moreover, we managed to get dew on dewless nights.
What makes our system special is that with the cheap materials we managed to get an impressive temperature difference and collect dew. We estimate the cost of our system by $20, and in mass produce it can be even cheaper.
A similar system from OPRU, the non-profit international organization for dew utilization, costs €750.
We used radiative cooling in our experiment to get dew, but it can be used for many more applications, from cooling down buildings to ice making.
So we really hope you enjoyed our video.
Now go out there and make some dew.